Okay, so we'll get started, and today we're going to look at the oxidation state ladder. So we'll go up from 0 to 4, and then back down, and we'll learn this in the context of reducing carbonyl-containing compounds to make alcohols. And so in the prior lecture, we learned the spectral signatures of alcohols. So again, we need to be kind of fluid in determining oxidation state, and then, from the data, has an oxidation occurred or was it a reduction? What specifically are we looking for? And we're going to categorize this again by looking at the carbon bearing the oxygen heteroatom. Is that going up or down? And so let's look at some main functional groups just to categorize things about what we're looking for, what is going to change. So in terms of the oxidation state itself, the hybridization, and then what should we look for. So we're defining oxidation state, and I'll refer to that as just OS, as the number of bonds from carbon to a heteroatom. And so that's anything other than C or H. And for our class here, we're concerned with the groups that come after carbon. So nitrogen, phosphorus, oxygen, sulfur, and then the halogens. So for this module, we're going to look at creating alcohols, ethers, and amines. So what do we mean by oxidation state here in this table? So if we consider the functional groups, so in the first or second column here we have methane, so CH4. That carbon has no heteroatoms attached to it, so we're just going to call it oxidation state 0. The carbon is sp3 hybridized. If we do a substitution of H for OH to make methanol, the oxidation state goes up 1. So we have a sigma bond from carbon to oxygen. The hybridization of the carbon stays the same. It's still sp3. If we take methanol and now we oxidize that carbon, so we're going to make the alcohol into a carbonyl. The oxidation state is now 2. And the hybridization had to change because we have a sigma bond and a pi bond from carbon to oxygen. We can further oxidize that carbon up to 3 with retaining the hybridization of sp2. Now that makes a carboxylic acid. So that's called methanoic acid. To complete the full ladder, and this is, we can only do this when we have one carbon. If the hybridization changes from sp2 to sp, we can get to oxidation state 4. And the example that's given here is carbon dioxide, CO2. So we have the carbon with 2 sigma bonds to 2 different oxygens, and then pi bonds. So with oxidation, you're still maintaining that rule of 4 bonds to carbons, but you need to pay attention to the hybridization of the carbon, because that's going to tell you whereabouts you should see things in the carbon-13 NMR. The oxidation state is a way to categorize reactions that we learn. So from starting material to product, is that oxidation state number increasing? So an increase in oxidation state, that's called an oxidation. Notice in these examples, I'm going to write a number above the arrow. So 0 to 1, 2 to 3, 1 to 3. So what I mean by the number above the arrow, the difference is just 1. So 1 to 3, that's 2. That's the stage of oxidation. So certain reagents can only increase the oxidation state by 1. Other reagents can do it a 2-stage oxidation. The reverse of that, a decrease, is called a reduction. So 3 to 2, 3 to 1, 1 to 0. So we have a 1-stage reductant, 2-stage, or a 1-stage. So conceptually, that's really what we're going to learn about, is the number increasing or decreasing. The challenging part here is, this number that I wrote above the arrow. Those are the different reactions. So for 1-stage oxidations or 2-stage oxidations, there's different reagents that will do it. And you really have to get a feel of what is an oxidizing agent and what is a reducing agent. So of those classes, then you have to categorize it again. Is it doing a 1-stage or a 2-stage? And you have to get a feel of, looking at the reagent. Is there stuff in there that indicates to me it's an oxidizing agent, or is it a reducing agent? And that, again, that gets back to the fundamental reactivity of nucleophiles and electrophiles. So we're going to look at making alcohols from carbonyl compounds. So as we saw, carbonyl compounds are oxidation states 2 or 3. Alcohols are oxidation state 1. So the reagents that we're going to learn, these are reducing agents. So conceptually, why does this work? So say you have some carbonyl-containing compound. We know that that bond is polarized because oxygen's more electronegative than carbon. It has 2 lone pairs. So the carbon is delta plus. That carbon then is electrophilic, meaning that the reducing agents have to be nucleophilic. So we'll talk about how these nucleophile reagents add to a carbonyl, this intermediate that they're going through, or I've shown O-, and then ultimately, how do we get the neutral alcohol? So in general, a pi bond is weaker than a sigma bond. So the nucleophile can attack the carbon, and it's going to break the weak pi bond. And through that, not only is the hybridization changing from sp2 to sp3, but then the oxidation state is being reduced. So in preparing alcohols, we have to look at the functional groups. Is it oxidation state 3 or 2? Are we doing a 2-stage reduction? So that's this first example. we go from 3 to 2 and then 2 to 1? Or are we just starting with some oxidation state 2 and then just reducing it down to the alcohol in one step? So here's a question for you. We have these categories: oxidation state 1, 2, and 3. So which choice best matches the functional group associated? What'd you say? It's not D, B. So B is in boy. So alcohol is oxidation state 1, aldehyde is 2, ester is 3. So of those functional groups, you're looking at the carbon bearing the heteroatom and then counting the number of bonds you see to the oxygen. So here's really what we're looking at for this sort of regime of making alcohols from carbonyl compounds. These are the ones that you know. So there's a line. To the left, we have the two functional groups that we know are at oxidation state 2. So aldehyde and ketone. And then the third row in that table is showing us the main IR location of the carbonyl stretch. To the right of the line there are all the oxidation state 3 functional groups. So we have a carboxylic acid, ester, acid chloride, anhydride, amide. And then notice the nitrile. It doesn't have a carbonyl, but it still has 3 bonds to a heteroatom. So it falls within this reactivity pattern. So our two ways of doing this. We have 2-stage reduction and 1-stage reduction. And ultimately, that's dependent upon what your starting material oxidation state is. So with OS3, remember those are acids, esters, acid chlorides. Then the other one, aldehydes or ketones, that's a 1-stage because we only need to go down from 2 to 1. We're going to learn 2 ways of making alcohols. The first way involves using hydride as the reducing agent. So on the periodic table up here, hydrogen has a proton, an electron. That's the neutral form of it. If you take away that electron, you get H+. If you add another electron, you get H-. That's called hydride. So hydride is a nucleophile because it's supplying the electrons in the mechanism. The carbonyl carbon is the electrophile because it's going to accept them. And once it accepts them, the oxidation state has to be reduced. The 2 most common reagents to accomplish this are sodium borohydride and the lithium aluminum hydride. And this is what I mean by when you're on an exam or the final exam or whatever, and you're looking at a reagent, do you have an intuition about its reactivity? So sodium borohydride, if we draw that out as a Lewis dot structure, we know that sodium has to be positive. So boron's the central atom. It has to be negative. And it's then bonded to 4 hydrogens. From our Gen Chem, sodium forms +1 cations, so whatever X minus has to be a -1 charge. The reason that boron is negative is because it's in this group here. Remember, it's that weird one where it doesn't form an octet. So it typically has bonds to 3 other things, but now that we have 4 bonds to it, it's going to be negative. So a way to think of that borohydride we kind of split it apart. We now have the neutral boron and then the negative hydride. So when I look at that reagent, there's no oxygens in there. So that tells me that can't be an oxidizing agent. It has to be a reducing agent because of the excess of hydrogen. Lithium aluminum hydride. Aluminum is right under boron, so it has the same sort of Lewis dot structure to it. And these are the most commonly used ones because they're both solid reagents. You can buy them, they're easy to weigh out. They're not terribly reactive with the atmosphere, so there's some safety issues, but not anything to preclude their use. So these reagents add H minus. But what if we want to add carbon? So carbon with a negative charge. Those are called carbanions. So we have some carbon with a lone pair and a negative charge. The negative charge is balanced by a metal, so M plus. Those type of reagents are called organometallic. They're prepared in reactions that we learned in Organic 1, where you took like an alkane and you did a radical CH substitution for some halogen. Once you have that, you can then do kind of a reversal where the halogen's removed and replaced with a metal. As you might imagine, when you have H minus and then carbon with a negative charge, those are pretty reactive. Every reaction that we run is carried out in a solvent, so a liquid that dissolves everything. We need to make sure that the hydride or the organometallic reagent does not react with the solvent. So your solvents typically have to be aprotic. So there's not acidic hydrogens floating around that will quench your reducing agent. So these are typically things like nonpolar alkanes, hexane, ethers, diethyl ether, or tetrahydrofuran, which is another type of ether. And so even though they have CH bonds, they're not acidic CH bonds that will react with our reducing agent. So let me just kind of show cheap mechanism here with some arrow pushing of how things are going to flow. If we start with this carbonyl containing compound, so that's a ketone. It's called propanone. What is the oxidation state of the second carbon atom in the chain? So it's oxidation state 2. If we reduce it, it has to go down to 1. So that makes 2-propanol. So sodium borohydride is the reagent that we'll use to do this. If we assign partial negative, partial positive to the carbonyl, we arrive at that based on electronegativity. And we're going to say that sodium borohydride is supplying H-. So the minus is attracted to the plus. So the arrow will start there, point to the carbonyl. Because we're making an H to carbon bond, we have to break an existing bond. So the electrons in the pi bond will then go up onto the oxygen. So right now, remember a negatively charged oxygen, that's called an alkoxide. So we still need to do one thing and supply a proton source, so H+. So a lone pair from oxygen will bond to that acidic proton. And this is typically done during a workup stage of the reaction. And so now we end up with our neutral alcohol. And we can confirm that through IR by looking for that broad stretch. So have you guys done thin layer chromatography in lab? So thin layer chromatography, or TLC, is typically used to analyze the progress of a reaction. So we have a starting material, and then we have a product. When you spot your starting material on the plate, you're then going to spot your reaction alongside it. And do you remember what you're looking for when you develop the plate? Say it again. Polarity. Yeah, it's the polarity difference of the functional groups from the starting material to the product. So on your plate, so in lab, we do this, we run 3 lanes. So we have a starting material lane, a reaction lane, Then we have a middle, which is called a co-spot. It's where you put the starting material and the reaction on top of one another. And then you elute it with solvent up to some line. So when you elute that, what would you expect to go further up the plate, the ketone or the alcohol? So the ketone would go further up the plate. And your alcohol wouldn't travel as far because now you have an OH group which can hydrogen bond. It likes sticking to the plate more, so it doesn't travel as far. So not only will TLC tell you about the progress of a reaction, it's also giving you an indicator about the polarity of what's happening in the reaction. So a little bit more in depth about that arrow pushing. Because we're starting with an sp2 hybridized carbon of the carbonyl, and remember that oxidation state can be 2 or 3, depending upon what these substituents are. The nucleophile, whether it's hydride or a carbanion, it attacks that carbonyl with a certain trajectory. And this parallelogram or rhombus or whatever it is meant to represent the plane of that carbonyl. So from that plane to the nucleophile, that angle is 109. The reason it's 109 is because now the hybridization in the product is sp3. So it has to attack at such a trajectory to mimic the change in hybridization. So in solution, when this thing's floating around, it doesn't like come from over here and attack. It's got to be like the perfect pass here where the quarterback sees that receiver on that angle. And the reason that's important is because when you think about what these R1 and R2 groups are, you can have things that are small or things that get really big. If they're really big and bulky, it's harder to get to that angle. So mechanistically, we would call that a nucleophilic addition. Either hydride or carbon is adding. And then you get to this intermediate where oxygen's negative. And this is where a little bit more of the nuance comes in, where it's important to classify, is that oxidation state 2 or 3? If it's 2, it goes to 1 and it's stuck. Can't do anything else. If it's 3, it goes into here, and then depending upon what R1 and R2 are, another thing can happen. And so I'll lay that out mechanistically on the next slide or two, where you get an elimination and then a second addition. That's how you can overall go from oxidation state 3 all the way down to 1. So paying attention to the oxidation state here. Is really going to be important about how you predict out where this thing stops. So in the top one, if you start with an aldehyde or ketone, you do the addition of the nucleophile, the oxidation state is already at 1. So nothing else can happen other than that oxygen gets protonated to your alcohol. If you start with oxidation state 3, that means this other group here is a heteroatom. That's how you're getting up there. So you either have a halogen, a nitrogen, or some other oxygen. And what is different now, this O- intermediate, a lone pair can come down and eliminate. So elimination is the formation of a pi bond. It'll kick that group out. And when it does that, it's now going to oxidation state 2. You started with 3, you're at 2, but 2 is still susceptible to being reduced. And because it's in the presence of reducing agents, it's going to get back up into this manifold here now, as if we were just starting with something that was at 2 already. So we do a nucleophilic addition, and then protonation if we start with oxidation state 2, which are aldehydes, ketones. For the other ones, addition, elimination, addition, and then protonation. Any questions? So for hydride reducing agents, we have the sodium borohydride, lithium aluminum hydride. I want to point something out so you don't call me a liar. Notice the solvent here for sodium borohydride is protic. This is really the oddball, and that's the only one where you're using either water or an alcohol. Everything else has to be either the alkane or the ether solvents. The reason this one uses these protic solvents is the sodium borohydride is kind of inert and it needs something to activate it, whereas the lithium aluminum hydride does not. So from the reagent, I have our oxidation states. And then we're going to use this stoplight system. So green means it will react. Red means it will not react. So what is sodium borohydride telling us? You can only react that with aldehydes and ketones. It's not strong enough to do anything at OS3. Lithium aluminum hydride it doesn't discriminate, it hits everything. So it's pretty reactive. The different colors tells you the difference in reactivity. So if we expand out, these things to the functional groups and look at each reagent, if we start with an aldehyde and sodium borohydride and it reduces it, does it make sense to you that an aldehyde always has to produce a primary alcohol? Same thing with lithium aluminum hydride, it's always primary. We start with a ketone, you're always ending up with a secondary alcohol. Notice for sodium borohydride, it does not react with any of the oxidation state 3 functional groups. Lithium aluminum hydride, on the other hand, does. And what class is it producing in all cases? It's producing primary because that carbonyl group is at the end of the chain. The ketone's the only oddball where the carbonyl group can be in the middle of the carbon chain. These last two, so amide and nitrile, when we start talking about amines, that's when we'll look at their reactivity and why they don't produce alcohols. Say you have this is a difunctional molecule. What's the oxidation state of the blue carbon?
2.
And what's the name of that functional group? And then what about the green one? What's that oxidation state?
3.
And what is the name of the functional group? Maybe a little light on the A, we'll call it an ester. So we have a molecule with 2 functional groups at different oxidation states. We're treating that with sodium borohydride. So what oxidation state does that react with? So only 2. So we found that it will only react with the aldehyde. So which of the products is the best choice here? So B is going to be the correct answer. So notice it didn't do anything to the ester. That oxidation state's retained. And so it reduced that carbon down. That's now oxidation state 1. And by the definition of an aldehyde, the carbonyl is at the terminal carbon. It already has an H. We're adding another H to it, so that has to be a primary alcohol. So the same molecule, but now the reagent's different, lithium aluminum hydride. So what do you think the answer for this one will be?
C.
So this is C. That will react with both oxidation states 2 and 3. See how that blue carbon already has an H? So it's oxidation state 2. it's getting a second one, so it's going from 2 to 1. The green one, oxidation state 3, it has no hydrogens, right? But it's ending up with 2. So again, what's happening is you get a hydride adding. This thing leaves, this O-methyl leaves to make an intermediate that's an aldehyde. And because it's swimming around in an excess of H-, it has to react with that and get further reduced. What is the usefulness of this? When you have molecules at different oxidation states, you want to have these different reagents or tools that can only selectively react at some of them. If we only had lithium aluminum hydride as the only reagent, we would always end up with, you know, the most reduced form of whatever oxidation state. There'd be no controlling it. So the sodium borohydride gives us some flexibility that it cannot react with acids, esters, or acid chlorides. So we won't talk about this for the current module, but the one coming up. So we made we've seen sodium borohydride can allow us to make B. Lithium aluminum hydride can allow us to make C. D is what we're starting with. But what about A? What if we wanted to make A? Can you see what the issue is? So lithium aluminum hydride, or LAH, it's always going to make that. But say we wanted to retain that oxidation state at 2, but take that to 1. So there's a strategy for doing that we'll learn in the next module. That just means to access product A, we have to insert some steps overall, but we can still make it. We're not just limited by the reducing agents we have. There's a strategy that we can put in there, still allow us to retain that aldehyde functionality. So that was the addition of H-. What about carbon? Say we want to do some reduction, but we don't need an H, we need some sort of carbon, or any sort of carbon we want, whether it's a linear chain, a ring, a branch chain. How can we make something that is C-? So carbanions. So in the type of bonds that we've learned so far, we've seen these nonpolar CH-CC, and then we've seen these polarized covalent ones where there's this heteroatom And the heteroatom's always delta minus, right? So that means the carbon's always delta plus. But we want to make something where now the carbon is minus. How do we make those? Conceptually, the process is just reversing the bond polarity. We're going to make carbon minus and then balance the charge with some metal, whether it's one of these group 1s, so lithium, sodium, potassium, or group 2, magnesium or calcium. That's going to be +1 or +2. And therefore, the carbon has to be the anion negative. The reagents are called organometallic. So organo is the carbon part, then we have the metal cation. They take this form, so M plus X minus. Think of like sodium chloride, like a salt. In sodium chloride, the chlorine owns that lone pair, so it's negative. For organometallic reagents, the carbon owns the lone pair, so it's negative. The carbon that's negative can have any hybridization, sp3, sp2, or sp. And so of those, there's different ways of making them. So depending upon what we want to make, whether it's sp3, sp2, or sp, the starting functional group is shown in that second row. So alkyl halides, aryl, that means there's an aromatic ring and one of the carbons is negatively charged. For sp, we have to start from a terminal alkyne. For sp3 and sp2, we're going to start with halides. And the reactivity order for generating them, iodine is faster than bromine, which is faster than chlorine. And typically we can't start with fluorine because fluorine is too electronegative to do this reversal. I would say the group 1 metals are the most common, so lithium, sodium, potassium. So for this group here, reactivity increases going down the group. So potassium ones are the most reactive, sodium less so, and then lithium the least. Have you guys done your Grignard reagent in lab yet? Sound familiar? Grignard. So you will do this in lab. You might have success, but you probably won't, just because, again, you're generating something that's very reactive, and you're not doing it under the most strict circumstances. So Mississippi's hot, it's humid, no matter what time of year it is. So you're going to make this reagent, and then just the humidity is probably going to quench a lot of it before you can even do what you want it to do. So the solvents, again, that you use are aprotic. They don't have acidic hydrogens. They're just there to dissolve things so that it's in solution and the reaction can take place. So the three categories here. according to the carbon hybridization that's bearing the lone pair, the negative charge. If we start with this alkyl bromide, so that's something you would use for an SN2 reaction, right? Bromine is a good leaving group. You could substitute it. And the reason that works is because the bromine's delta minus, that carbon's electrophilic. But what we want to do now is reverse the polarity. We want that carbon to be minus. So it turns out if you take something like that and treat it with lithium metal, so lithium, when you buy it, it typically comes as like a wire, and it's soft enough you can cut it with scissors. So you have a slight excess of that. Lithium in its elemental form, since it's in this group, it has one electron. It wants to give up that electron. So we need it in excess so that there's a total of 2 given up. And you see this carbon-bromine bond? It's essentially giving that carbon 2 electrons, so that ultimately you have C minus Li plus. I've written this as a covalent bond, but the way to think about it is now that carbon has a lone pair, so it's negative, and the lithium is positive. And then we can balance off the other elements by forming lithium bromide. So what you'll do in lab is you're going to take an aryl halide. So the benzene ring, aryl is just another short term for aromatic. Now the carbon's sp2 hybridized. Magnesium's in group 2, so it has 2 electrons. It's going to reverse the polarity of that bond. So that your carbon is now negative, the magnesium's positive, and notice the stoichiometry here, because magnesium's group 2. One of the anions is carbon, the other one is bromide, Br minus. So the last type of hybridization that we need is sp, and that's going to come from a terminal alkyne. So to generate these, we do an acid-base reaction. The CH there is pretty acidic at 25. We have this reagent, sodium hydride. It will abstract that H to generate an sp hybridized carbanion. So those are the 3 general methods for generating these things from starting materials where the carbon hybridization is different. So let's start putting some of this to practice to see how we can make different classes of alcohols. And the way that I want to show you this first, it's using this arrow here. Which is called retrosynthesis, meaning that we're looking at our target. What do we want to make? We want to make that which is called benzyl alcohol. The carbon bearing the OH, that's a primary carbon. So when we think about it, we want to make this carbon-carbon bond. Since that carbon is bearing the oxidation state of 1, when we think backwards, it has to start at an oxidation state of 2. So that's the electrophile. And the organometallic is the nucleophile. So from the target, those are the things that we could start with. If we go into lab to do this, we could start with bromobenzene, treat it with magnesium metal and ether. That would generate the nucleophile. This aldehyde, 1 carbon formaldehyde, that's our electrophile. So we have carbon minus, that is going to attack that. We're going to break the pi bond. Then on workup, that's how we get our neutral alcohol. So formaldehyde is a good source of 1 carbon. There's another reagent we can use that will make primary alcohols, but it has 2 carbons. So our target now is 2-phenylethanol. And this is the bond that we want to consider making. So the dashed line means when we think backwards, we're going to break that. And the reagent that we end up with as the electrophile is called ethylene oxide. So that's an ether. And the reason we can do it is because it's a 3-membered ring that's strained. So it's pretty reactive. And the nucleophile will want to open up one of those bonds. So even though we're starting at something with oxidation state 1 and 1, one of those bonds breaks, so a reduction does happen. So in the same sense, we can assign the polarities. Again, that carbon's negative, so it's attracted to positive. And then it's going to pop open one of those CO bonds. So that arrow has to point to the delta negative. So we would monitor this by TLC to see eventually, okay, things have changed enough. I don't see any more conversion. So now I'm going to adjust the pH during the workup by adding acid to get that H of the alcohol. So that's two ways of making primary alcohols using carbanions. If we wanted to make a primary alcohol with a hydride reagent, that's when we would use sodium borohydride in an aldehyde or some OS3 plus lithium aluminum hydride. So what if our target is now a secondary alcohol? So the carbon bearing the OH, that's called the carbonyl carbon. So it's an alcohol. So oxidation state 1, it's classified as secondary because you have a carbon and a carbon. So one way of doing this in terms of thinking backwards, if we break this bond and we say we want that carbon to be negative, so this carbon would have to go up in oxidation state, meaning that it has to come from this aldehyde as the electrophile and then that organometallic as the nucleophile. So where are we going with this? If you look at any alcohol, the carbonyl carbon has, aside from the OH group, it has 3 things bonded to it. When you classify those things, you get primary, secondary, or tertiary. So on this slide, I've shown you one way to think about making this. What would be another way of making this using a carbanion reagent? So I'm going to draw this dashed blue line. Say that is the way I wanted to go about making this. So one part of that line is going to be the nucleophile. The other part is the electrophile that has the carbonyl. So when I do that, I can get another pair. The nucleophile now would be one carbon atom. And the electrophile would then be this aldehyde. So now that ring is already in place. That's the electrophilic carbon. Now what I need to do is add one methyl group to get to my target. So that's 2 ways of making this alcohol. There'd be a third way. So the first one is using that as C minus. The second uses that as C minus. The third one would use hydride, H minus. If we wanted to start with a hydride reagent, what functionality would the starting material of that electrophile have to be? It'd have to be a ketone. Because now in the ketone, you're retaining that carbon group and that carbon group, and you're just adding H to it. So if you start with a ketone and you add H, you're always going to get a secondary alcohol. So for tertiary alcohols, I'm going to give you a special case here. We can identify the oxidation state 1 carbon that's bearing the OH. Then look at the substituents bonded to it. You have an aromatic ring, and then these two other groups are the same. What that tells us is we can start with something that is oxidation state 3, and it will add 2 of this same group to reduce it all the way down to oxidation state 1, which is now a tertiary alcohol. Again, the reason that happens, you're going to get one addition that happens. That's going to form a ketone. The ketone's in there swimming around with these nucleophiles, so it's going to undergo a second addition. And because they're the same group, that's how you end up with this symmetric alcohol. So whenever you see, that tertiary alcohol, 2 of the groups are the same, you can tell it's coming from something that's OS3. See where, okay. So to preface, the next slide and kind of put this all in a package here. If you look at your starting carbonyl group, so these would both be oxidation state 2. The acid, the ester, the acid chloride, those are oxidation state 3. So if you're starting with these and you're adding a carbon anion to it, what is it going to produce in terms of the alcohol class? An aldehyde will always produce a secondary alcohol. A ketone will always produce tertiary. You start with a carboxylic acid, you will never produce an alcohol because it's going to react with the acidic OH first. So we call that a quench. So you either have to start with an ester or an acid chloride, and those produce tertiary alcohols. Typically, you'll know if you started with one of these because 2 of the substituents will be the same. So once we know what the reagents can do, their reactivity, then we can start thinking about the product and drawing up a blueprint of, okay, how can we actually make these things? We're at here. So for any alcohol, so the carbon bearing the OH, that's the carbonyl carbon. There's 1, 2, 3 substituents. And then based on what those things are, the alcohol is primary, secondary, or tertiary. So consider this molecule that's shown to the bottom left. What class of alcohol is this? So that's tertiary. And then when you look at the substituents, you have a phenyl ring, ethyl, and methyl side chain. So they're all different. In terms of a strategy, how can we make this thing? There's 3 ways of making it. So we can do these different dissections where we end up with different carbonyl groups, different organometallics. And so on the next slide, what we'll do is look at this. What are the 3 ways we can get back to starting materials of making that? So say I want to make that bond connection. So whatever part of the molecule retains that carbonyl carbon, it has to go up in an oxidation state, because the product is ending at 1, meaning we have to start with 2. So what functional group would this be? What name? Not the name of the molecule, just overall the general functional group. If that carbon goes up to 2, what would this be? So when we look at that carbon, it's going to be bonded to a carbon and a carbon. So that's going to be a ketone. So the ketone that we would start with would be that one. And since we want to add 1 carbon to it, that could be an organometallic we use to make that bond. Just go clockwise. If we wanted to now make that one, this would be a second way. That's a different ketone now. Now we need something with 2 carbons. So that could be the organometallic. Then the third one is the last disconnection. Still a ketone, but now we're using an aromatic ring as the nucleophile. So those are 3 ways we can disconnect any alcohol. And from that, if you had to practically do this in lab, or if it was part of your job of buying these starting materials, you'd have to look at the cost of each. You'd want to minimize the cost. Also consider any safety issues that would be involved. So even if you're not too jazzed about organic chemistry and you like business, people do this in the pharmaceutical industries. They source these things. What's the cost of buying it? How does that impact the final product? How do we maximize profit? So this sort of analysis is pretty important economically. And so we're out of time. So what we'll start with on Wednesday is the reverse. We've done reductions. Now we're going to take alcohols and oxidize them to carbonyls.